Today we're looking at a paper called Reverso, Efficient Time Series Foundation Models for Zero-Shot Forecasting by Xinghong Fu, Yanhong Li, Georgios Papaioannou, and Yoon Kim. And they're from MIT, the Allen Institute, and Quab Research.
Yeah, and it addresses a pretty massive inefficiency in the current AI landscape.
Yeah.
Right now, the whole trend in time series foundation models, or TSFMs, is just aggressive scaling. Like, we're seeing models like Shimax or Moirai pushing into the hundreds of millions, even billions of parameters.
Operating on that assumption that bigger is always better, the classic scaling law.
Exactly. But Reverso completely flips that script. I mean, this isn't a billion parameter beast. It's a family of models, nano, small, and standard, and they range from just 0.2 million to 2.6 million parameters.
Which is tiny.
It's tiny. And that is the key result here. Despite being orders of magnitude smaller, we're talking literally 100 times smaller than some of the baselines Reverso matches, or even outperforms those massive transformer-based models on benchmarks like GiftEval and LTSF.
It effectively redefines the whole performance efficiency parade or frontier.
Right.
So what's the secret sauce? How are they doing this?
It really comes down to abandoning this standard large transformer architecture.
Okay.
Instead, they use a hybrid approach. They interleave long convolutions with linear RNNs, specifically DeltaNet.
Okay.
And then they combine that highly efficient architecture with a very specific optimized training recipe involving extensive data augmentation and synthetic data generation.
All right, so that is a huge claim, right? That a tiny model can beat the giants just by being smarter about the architecture and the data. So let's step back and dive into the context for this deep dive, because as you know, if you follow our AI paper podcast series here on YouTube, we've seen this total explosion of foundation models for time series recently.
We really have. I mean, historically, forecasting was entirely statistical. You'd use ARIMA or exponential smoothing.
Right, the classic.
Yeah. Then came the deep learning wave with RNNs and LSTMs. But recently, following the massive success of GPT in language, everyone just shifted to foundation models.
Yeah.
You have TimesFM from Google, Chronos from Amazon, Laglama, Moirai.
The logic there has been pretty straightforward, right? Just throw more data and more parameters at the problem.
Exactly. The assumption, which is validated by papers like the recent Sun et al. Work on G, is that zero-shot forecasting capabilities essentially emerge from scale.
You train on a broad data set, you make the model huge, and boom, suddenly it can predict a time series it has literally never seen before via in-context learning.
Right, but there's a fundamental contradiction there.
Yeah, because language is incredibly complex. You've got nuance, sarcasm, multiple languages, syntax. But a time series, do we really need a billion parameters just to predict a sine wave or like a weather pattern?
And that is precisely the question this paper asks. In computer vision or NLP, scaling seems almost infinite. But in time series, the signal is often much lower dimensional. The authors argue that while scaling does work, it is not strictly necessary to get state-of-the-art performance. You're basically burning a massive amount of compute for very marginal gains.
So the mission of Reverso isn't just to build another model. They want to find a recipe for efficiency.
Yes.
So let's unpack this architecture, because they made some very specific choices. They aren't just shrinking down a transformer.
No, they are completely redesigning the core block.
Right.
First off, the input handling is super clean. They take a time series sequence, they normalize it to a 0 to 1 range,
Okay.
and they project it into dimension D.
And they explicitly avoid complex metadata embeddings, right? Or specific frequency features.
Correct. They want the model to be entirely general, because if you start hard-coding frequency embeddings, you might inadvertently bias the model towards specific types of data.
Like hourly or daily data.
Exactly. By keeping it as a raw numeric sequence, it stays flexible for any domain.
Okay, so the sequence goes in. Now we hit the sequence mixing block. You mentioned this is a hybrid.
It is. They stack blocks that alternate between two distinct types of layers. The first is long convolutions.
And when we say long, how long are we actually talking?
The kernel size equals the sequence length L.
Wow.
Yeah, in standard convolutional networks, you usually have these small kernels sliding over the data step by step. Here, the convolution looks at the entire history all at once.
But wait, doesn't that get computationally expensive really fast?
It absolutely would if you computed it the naive way, but they use the fast Fourier transform, the FFT. By moving the math into the frequency domain, the complexity drops to O of L log L.
Which is significantly faster than the quadratic cost of standard attention mechanisms in transformers.
Precisely. And convolutions are inherently excellent for recall. They're great at remembering specific patterns across the whole context. But they do need a partner. And that is where the second layer comes in linear RNNs. Specifically, they use DeltaNet.
DeltaNet. That sounds like a sci-fi villain network. What is it actually doing in this context?
It's basically a linearization of an RNN. It learns state transitions using query, key, and value vectors, which is similar to attention, but it updates a recurrent hidden state S sub t. This allows the model to process the sequence information sequentially, but much more efficiently.
And looking at the paper, they add this really interesting trick they call state weaving.
Yes, this is a very cool technical detail. In a standard stacked RNN, the layers are somewhat isolated in terms of their state. But here, they take the last time step of the previous layer and they add it to the first hidden state of the current layer.
So they're effectively stitching the context together vertically right through the network.
Exactly. It significantly improves the modeling of bidirectional context. It helps the model understand the overall flow of the data much better than isolated layers ever could.
So we have the long convolutions for global pattern matching and the DeltaNet for sequential state updates. And then between these, I assume they just have standard channel mixing.
Right? Just standard MLP layers with an expansion factor of 4. That's essentially the muscle of the network, processing the features at each time step.
Now here's where it gets really interesting to me. The body of this model is not a transformer. It's this highly efficient hybrid conv RNN thing. But then we get to the output, the decoder head.
And surprise, it uses an attention mechanism.
Right. Why? If you've gone to all this trouble to avoid attention in the main body just to save compute, why put it back in at the very end?
Because a simple linear head just wasn't enough. The decoder needs to generate query vectors to look back at the context representations the body created. It attends over that compressed context to predict the future chunks. In this case, they predict a patch of 48 points at a time. The attention mechanism at the head gives them that final boost of precision in selecting exactly which historical features matter for the immediate future.
It's almost like the body digests the information into a highly efficient format, and then the head uses a spotlight to pick exactly what it needs for the forecast.
That's a perfect analogy, and their ablation studies back this up completely. They compared this hybrid the conva plus DeltaNet against pure DeltaNet, gated linear attention, and pure attention with RoPE. The hybrid approach consistently won out across the board.
Okay, so that's the engine. But as any ML engineer knows, having a good architecture doesn't guarantee a good model. You need the right data. And the paper heavily emphasizes that the architecture is really only half the battle. The recipe, the data handling, is the other half.
This is so often overlooked in research papers, but here they are very explicit about it. They trained on the GiftEval pre-training dataset, which consists of about 4.5 million time series.
But not all time series are created equal.
Far from it. Real-world data is famously messy and highly imbalanced. You have massive data sets in there like Buildings 900K or Era 5 weather data that completely dominate the count. If you just train on the raw pile naively, your model just learns to predict building energy loads and temperature changes.
It overfits to the dominant domains, so how did they balance it?
They recomputed the strides. Essentially, for the massive data sets, they skip through them faster by increasing the stride so they don't oversample them. They strictly capped samples at 100,000 per epoch per data set.
Which forces the model to see a true diversity of domains, not just the ones with the largest file sizes.
Exactly. And then comes the augmentation pipeline. For a model this small, remember, we are talking about literally a few megabytes of parameters. Overfitting must be an absolute nightmare.
Oh, for sure. So they implemented a rigorous pipeline. They use downsampling to teach multi-scale learning. They use amplitude modulation to handle different scales of values.
And I see they use flips, too.
Yes, vertical and horizontal flips. Vertical flip is sign inversion, so predicting negative x instead of x. Horizontal flip is time reversal. This forces the model to learn the actual structural dependencies rather than just memorizing a specific sequence direction or magnitude.
And censoring.
Yeah, that's clipping the top and bottom of the data. It makes the model robust to anomalies. If you have a sensor glitch in deployment that spikes to infinity, you don't want the model to completely crash. Censoring teaches it to handle those outliers gracefully.
Plus mix-up applied at the batch level. They're really throwing everything at this thing.
They are. But the most interesting part of the data recipe, for me at least, is the synthetic data.
Oh, right. They generated 1 million synthetic series using something called kernel synth.
This part is fascinating. They use a kernel bank. Imagine mathematical primitives, a constant line, a linear slope, an RBF curve, a periodic wave.
Like Lego blocks for time series functions.
Exactly like that. They randomly compose these together, so they might add a linear trend to a periodic wave, then multiply it by an RBF, then they run a Gaussian process over that whole composition.
So they are mathematically manufacturing time series that look complex but have an absolute underlying mathematical ground truth.
And they don't stop there. They add spike processes and TSI, which is trend, seasonality, and irregularity, to mimic the inherent messiness of the real world. This synthetic data acts as a perfect regularizer. It teaches the model general, fundamental forecasting principles that might not exist clearly in the noisy, real-world data.
Wow. So we have a highly efficient hybrid architecture trained on a balanced, heavily augmented, and synthetically supplemented data set. Now let's talk about actually using it. Inference.
The deployment phase. This is where zero-shot performance actually matters to you as an engineer. You have a model, you give it a brand new time series, and you want an accurate forecast.
Right, and they mentioned two strategies here that really caught my eye. The first is flip equivariance.
This ties right back to the augmentation we discussed. At inference time, they pass the original sequence X into the model to get a forecast, but they also flip the sequence to negative X, get a forecast for that, and then flip the result back.
And they just average the two?
Yes. It mathematically cancels out certain biases in the model. It consistently reduces forecasting error without changing the weights at all. It's essentially free performance.
That is such a simple trick. But the second strategy seems even more critical for real-world use, smart downsampling.
This addresses a fundamental limit of small models. The model has a hard context length of L equals 2048. But what if you are trying to predict a seasonal pattern that repeats every 4,000 steps? The model literally cannot see one full cycle.
It's flying blind to the seasonality.
Exactly. So before inference, they run an FFT on the input data. They look for the dominant frequency peak. If that peak, the period, is longer than the context window, they automatically downsample the input.
So they squish the input by a factor of k, so the entire pattern fits inside the 2048 window.
Exactly. If they downsample by 2, a 4,000-step pattern suddenly becomes 2,000 steps. Now it fits. The model can see the full cycle, make the prediction, and then they just upsample the forecast back to the original resolution.
That is brilliant. It's like stepping back from a massive painting to see the whole picture before you try to paint the extension of it.
It visualizes perfectly in the paper. They show a trapezoid wave. Without downsampling, the model just sees a line going up and has no idea it's supposed to come back down. With downsampling, it sees the previous trapezoids and nails the forecast perfectly.
Okay, we have built it up. Does it actually deliver? Let's talk numbers.
The results are stark. On the GiftEval benchmark, the Reverso 2.6M model achieves a Mayes mean absolute scaled error of 0.711.
For our listeners who don't have the leaderboard memorized, put that in context.
Sure. It beats flow state, which is the exact same size. It beats TTM, which is 1 million parameters. But impressively, it is highly competitive with Moirai B, which has 91 million parameters, and Kronos B, which has 200 million.
So a 2.6 million parameter model is actively trading blows with models nearly 100 times its size.
Yes. And if we look at the really tiny one, Reverso Small, which is just 550,000 parameters, it still gets a MESAs of 0.726. That outperforms many of the much larger baselines.
That is incredible efficiency. What about the LTSF benchmark? That's the zero-shot transfer test, right?
Correct. Testing on datasets like electricity, weather, ETH1, and H2, Reverso beats Sundial, which is 444 million parameters. It beats Timer XL, which is 84 million.
It really validates the whole hybrid approach.
And specifically, the paper notes that the hybrid architecture shines in long horizon forecasting. Pure transformers sometimes struggle to capture those super long dependencies efficiently, or they just get lost in the noise. The long convolutions in Reverso seem to anchor the model on those broad trends very effectively.
We do have to play devil's advocate, though. What are the limitations? No model does everything perfectly.
True. The biggest one right now is that it is univariate.
Meaning it only looks at one variable at a time?
Right. It takes one series and predicts its future. It doesn't look at cross-channel dependencies. Something like Kronos 2 handles multivariate data, where different variables actively influence each other. Reverso isn't there yet.
And I noticed they mentioned performance on very short sequences.
Yes, on very short sequences, it lags slightly behind the massive foundation models. The large models, with their massive memory capacity, seem better at picking up micropatterns in highly limited data.
Also, it focuses entirely on point prediction.
Yeah, it predicts a single value optimized for MAE loss. It doesn't natively give you a probability distribution or uncertainty bounds, though the authors do note you could bolt on conformal prediction to get that if you needed it.
Still, despite those limitations, the implication of this paper feels really significant. It feels like a turning point.
It reminds me of the MobileNet moment in computer vision. For a long time, vision models just got bigger and deeper, VGG, ResNet. Then MobileNet came along and said, hey, if we use depth-wise separable convolutions, we can run this on a phone with 90% of the accuracy.
Or the distillation era in NLP.
Exactly. We are seeing this solid proof that you don't actually need a supercomputer to do the job if, and this is the big if, you design the architecture and the data pipeline intelligently.
It also links directly to what we're seeing in LLMs right now with things like Jamba or Zamba.
The return of the hybrid. We spent 5 years thinking attention is all you need. Now we are realizing, actually, attention is really expensive. If we mix attention with SSMs or RNNs or convolutions, we get far better efficiency. Reverso is bringing that exact same realization to time series.
It's exciting because it lowers the barrier to entry for everyone. If you can train a state-of-the-art forecaster with 2.6 million parameters, you don't need a cluster of H100s. You can run this on a standard GPU.
You could run Inference on a laptop easily. It completely democratizes high-quality forecasting.
So to wrap this up, Reverso proves that scaling isn't the only path forward. A 2.6 million parameter model interleaving convolutions in DeltaNets can legitimately replace 200 million plus parameter transformers for time series.
It's a massive victory for precise engineering over brute force compute.
Which leaves us with a final thought for you to chew on. If a model 100 times smaller can match state-of-the-art performance simply by optimizing the architecture and training recipe, how much intelligence in our current giant AI models is actually just wasted parameter space?
That is the multi-billion-dollar question. See you in the next paper.